Well, one last thing we need to do for the N-Slit diffraction pattern is to get the case where the widths are finite and not negligible. We can't treat the slits as mathematical points. And that we'll do by comparison to the double slit. We found that for the double slit that we got this expression here. Beta is related to the slit width B. So K over 2B sine theta. And alpha, remember, was related to the separation between the centers of the slits. So the slit separations. Pretty clearly, as one way to look at this is as beta goes to 0, then this becomes 1 here, and we get the negligible slit width. If B goes to 0, then beta goes to 0, and then we just get the interference pattern for point-like slits for the double slit. For N-slits, we found a similar relationship. We found this relationship here. Again, alpha was the Ka over 2 sine theta. The only difference was, and also we showed that this in the case of two slits reduces to this formula. But it's pretty obvious that the impact in the double slit of the slit width was just this factor here, this modulation term that's out front. And that really hasn't changed when you have a finite slit width, even though you have n of them. Each slit has this contributes to this factor here that factors out. And you can go through the math. I think your book indicates it. It gets pretty complicated, but I think really just by analogy, all we need to do to bring our point-like slits up to finite width slits is to have this slit width factor in here. So, and in fact, that's what you get with a detailed calculation. For N-slits with finite width, one gets the intensity is I naught, sine beta over beta squared, and then this is the interference term between the various slits. And again, in both of these, we have a similar form for alpha and beta. You just, for beta, one has the slit width, and for alpha, one has the distance between the equally spaced slits, the distance between adjacent slits, the centers. Well, one can start plotting these again for various values of n, and I think I've got some of those. Yeah. Here is a plot of n of A equal to 4 and B equal to 1. So the distance between centers, you notice, is pretty much on the same order as the width of the slit. The widths are a little bit smaller in this case. One has the envelope function, and that's this. That's that central peak that occurs from this term, from that sinc function squared. And then you have the other terms, which would go all the way up to the top here each time, except they don't in the two-slit formulation. Right? If B is negligible, then these would all go all the way to the top, and you would get that usual case for just the point-like slit interference for two slits. But instead, if they don't go all the way to the top for these subsequent ones, they're modulated by the slit width diffraction pattern. For four slits, well, we've seen what that would do. Ordinarily, these would come all the way up to the top. That was our previous segment's results. But again, we're modulated by the slit width factor, that sine beta over beta all quantity squared. And that's this dashed line, and so when it comes up to the next relative maximum, it doesn't go all the way up to the top, but is truncated here, and so on. Again, we've got four slits, and so 4 minus 2 is 2, so we have 2 intermediate relative maxima in between, but they're substantially reduced. If you go to 8 slits, even more so. Again, if a B were effectively 0, okay, then these would come all the way to the top, but this sine beta over beta squared term modulates those, and so they don't go all the way up top, but just to that relative maximum. Again, there's 8 slits, and so there should be 6 relative maxima in here. Let's see if there are 1, 2, 3, 4, 5, 6. Yeah, so again, it's probably worthwhile and carrying these out to this next one. Remember, there's another comes down, and there's another hump way out here, but it's 4% of the central peak. But it's probably worthwhile to take out a plotting package and plot some of these for different angles, and get the following. And you'll have to choose some ratio to do it as well, some ratio of A's and B's. Well, as you can tell, what happens to these is that these higher orders, you get these intermediate ones, they get suppressed, and you get these the interference terms, they get enhanced, but they still don't come up. Most of the energy is not going into these intermediate relative maxima, but into these primary interference maxima.